Okay, why don't we get started? This is going to be the last lecture for Unit 5s, and it's going to be fairly short. It's on intermolecular forces. Now, your test is going to be available hopefully this evening, sometime. It could be late, but your test 5 should be available sometime today and then due on Saturday, as usual, on midnight. All right, are there any questions going into our lecture today? Okay, so let's jump into it here. Okay, what I want to talk about today is something called intermolecular forces. And it's kind of it's a non-mathy kind of thing, but it's a concept used to describe how molecules interact between other molecules or between themselves. And it has to do with a number of things. So let's start. I want to define a concept I've already defined once a while ago, but I want to reintroduce it. Excuse me. That's electronegativity. Now, electronegativity is a tendency for an atom to attract a neighboring atom's electrons. And that could be explained looking at the electronic configuration, looking at subshell stabilities, et cetera. But basically, if we look at a chart here put together by Linus Pauling, he put together these relative values of electronegativity. And you can see that fluorine here is really got a 4 versus relatively to say cesium down here. 0.7 versus 0.4. So then fluorine at 4 is much stronger of an electronegativity atom than things down here. So basically we have a trend, and that trend is this for increasing electronegativity. Now, come on, don't cough. Cooperate, cough. Okay. Normally we think of electronegativity in terms of atoms attached to another atom or a molecule. And so you've got a difference between electronegativity if you have more than one atom. In fact, you have something called the electronegativity difference, and that creates something called a moment or a dipole moment. Now, what that means is there's a skewed number of electron attraction to one of the atoms more so than the other. Now, if we look at the difference between, let's say, let's look at a couple molecules here. Let's look at, well, let's look at nitrogen. Okay, nitrogen has got 2 atoms of 2 atoms of nitrogen. I've been in cough all day. So their difference in electronegativity is going to be 3 minus 3. So N2 has no dipole or dipole moment. That means it's pretty non-polar molecule. Okay, if we look at another molecule, let's look at water, okay? And if we just look at one part of water here. So we have a delta electronegativity of oxygen, which is 3.5, minus hydrogen, which is 2.1. That's 1.4. Now, in terms of electronegativity differences or dipole moments, that's a big deal. That's a lot. And so let's look at one other molecule. Let's look at let's look at cyanic acid. Very, very poisonous. Carbon's got 2.5, nitrogen's got 3.0. So these molecules have a very different set of electronegativity differences. Hence, their polarity is also very different. If you have a molecule with electronegativity differences that are great, you have a molecule that has electron densities that are skewed to one side of the molecule or to another, which creates a disparity in the evenness of the negative charge of the electrons around the molecule. Okay. So if we were to look at a continuum from electronegativity difference of 0 all the way out to 4, there's going to be a continuum. There's going to be no discrete areas, okay? And over the years, we've drawn a kind of an area that is fuzzily right here. It's 0.5, not 0.5, but 0.5. And we're declaring that anything over 0.5 is considered a strong enough dipole to be polar. The farther you get away from 0.5, it becomes more and more polar. The closer you get to 0, it becomes less and less polar. So if we were to look at the types of dipoles, there are 3 main types. There's something called Ionic, which is the strongest. There's permanent dipole, and that's where an electronegativity difference is greater than 0.5. And then we have something called a temporary or a London dispersion force type of dipole. Okay, and it's the weakest. Okay. If we look at the strongest, it's called a ionic or ionic dipole interaction. That's where you've got a strong polar molecule like water. So we have an aqueous solution of table salt. Okay, so we have a hydration boundary around the anion chloride and a hydration boundary around the cation sodium. Okay, now this is going to create extreme polarity because it has huge differences in electron dispersion. Okay, we have a really strong molecule. Water, like I showed you up here, is 1.4, very strong. And we have chloride, which is strong to start with, and then it becomes ionic, so it becomes even stronger. So very, very strong molecules in this ion dipole interaction. And that's why it's the strongest. It's because we have ions involved here. They're not movement or attraction of electrons, they're actually transfer of electrons. It's very, very strong. Now, this is why ionic compounds are so soluble in water, because water is very polar. And ions are extremely polar because they actually have a charge to them. So they're very, very attracted to the water molecules because they're strongly dispersed electrons. Hence, they attract each other. Okay, that would be the strongest here. Okay, I've already talked about this guy here. That would be like when we have carbon and a nitrogen. Or, and by the way, if we look at this, so carbon hydrogen is 0.4 difference, so it's not considered very polar. Okay, how I got that is I'm looking at hydrogen's 2.1, carbon's 2.5. Okay. Now, whenever we have hydrogen involved, and it's bonded to nitrogen, oxygen, fluorine, that's when we get something called a hydrogen bond. And it's significantly stronger than a non-hydrogen bond, okay? So we kind of lump them together. We have just a plain old dipole-dipole bond or permanent dipole. And then if the hydrogen is involved and it's bonded to nitrogen, oxygen, fluorine, it's considered a hydrogen bond and it's much stronger. Okay, so we have super strong ionic. Next down would be hydrogen bonded permanent. Then dipole-dipole. And lastly, we have something called London dispersion forces. London dispersion forces, people usually say they're temporary. And what I mean by that is, if we were to look at lithium, and lithium nucleus with 3 protons in it and some number of neutrons depending on the isotope, and we have 3 electrons running around. And those electrons are never in the same place at any given time. So here we have an electron-proton dipole. We have an electron-proton dipole. We have an electron-proton dipole. Now, the thing you need to know about dipoles they are directional. And they have strength. Okay, some people like to call this a vector. Okay, so we have a certain strength dipole going this way. Let's see, let's draw it differently here. We have a dipole going this way. We have a dipole going this way. Now, if these were perfectly aligned, they would cancel each other. Okay, so that's time 1. At time 2, these electrons are in a totally different place. They could be like this. So then we would have dipoles that look like that. Okay. At time 3, my point here is that at any given time, there's going to be a dispersion of electrons and they're not perfectly balanced to cancel each other out. So you're always going to have a net dipole. And it's always going to be changing. That's what they mean by temporary. And London dispersion forces or dispersion forces are weak because these are really small little dipoles. Okay. So importantly, all molecules have London dispersion forces, no exceptions. Okay, all molecules have London dispersion forces. So if I was to ask you, what are all the IMFs for this molecule? Well, we have CHs, we have CNs, and we have NHs. Okay, and I'm going to ask you then is, and each one of these you can say the same thing. Okay, so we have CHs, COs, and OHs. CHs, COs. Okay. Now what you can do, you can analyze these guys looking at each pair of atoms and determine how strong they are. In other words, how many CHs are in this molecule here? Well, we have 3. We have 1 CN and 2 NHs. Here we have 3 CHs, 1 CO, 1 OH, and here we've got 10 CHs and 2 COs. Of these 3 molecules, which ones do you think are the strongest in terms of polarity? Oh, there's one more here too. Let's do this one here too. So we have CO, CC, and we have a 1 CO, 2 CCs, and 6 CHs. Okay, so let's look at these molecules now. This is a typical question. Analyze the intermolecular forces of this molecule. Okay, well, CH we've already determined is 0.4. Okay, that's C is 2.5, H is 2.1. Okay, so that's 0.4. Okay. What about Cn? Okay. Okay. So Cn is going to be 0.5. Okay. N is 3, C is 2.5. And NH, okay, N is 3, H is 0.4. So that's 9. Okay, CO down here is 1, because it's 3.5 minus 2.5, and OH is 3.5, 2.5, that's 1.4. And CC is going to be 0 because we have 2.5 minus 2.5. So these are the delta electronegativities for these pairs of electrons, okay? Now, looking at our table over here, okay, the hydrogen bonds are stronger than the dipole-dipole, okay? So if we were to analyze these bonds, first of all, they all have LDF, right out of the chute, all have LDF. Okay, so 0.9 is high. 0.1, I mean 1.0, 1.4 is high. All the ones that are above 0.5, I'm highlighting. Okay, so of these molecules then, which has the strongest delta En? Well, probably this one, because of this guy here. Then this one. And between these two now, it's kind of a toss-up. I would say they're kind of even. This one would probably be a little stronger because it has 2 COs. This one has 1 CO. So basically, you're just looking at how strong the delta electronegativities are. Okay, excuse me. Now this comes in, is really important in everything. It's important in the body. It's important just in our environment, because we have, this is methanol. This thing has got, it's very, very polar because of all the strong dipole moments it's got in it. This is called diethyl ether, and it's not particularly polar because it doesn't have a lot of strong polar combinations in it, or dipole moments. So that's the reason why we look at intermolecular forces, is we look at things like, for example, our body. Our body is mostly composed of water, very, very polar. And the reason I say that, I want to just redraw that molecule. Okay, this has got 2 OHs at 1.4. So the only combinations water has are hydrogen bonds. So it is very, very strong polar molecule. So our body is composed of this extremely polar water solvent. And our body chemicals, hundreds of thousands of molecules in our body have to interact with this very, very polar solvent, water. So our body has put together some structures that allow it to separate certain areas of water from other areas of water. And it does it by putting between water barriers something that's non-polar, or something that has very few strong dipole moment combinations. Okay, and that's called a membrane. And the only reason a membrane works is because of intermolecular forces, period. And it does it by keeping the polar water on one side of the membrane and the other polar molecules on the other side of the membrane. And it's got something called a transport mechanism to allow things to pass through it when it wants to. But in general, our body has to somehow figure out a way to separate these very, very polar parts of reactions that are going on in water and keep them very separate. Otherwise, it'd be a big mismatch. So our body is taking advantage of this intermolecular force differences in molecules to isolate certain water reactions from another water reaction. Okay, and that's why it's important to understand intermolecular forces. Okay, and that concludes our unit 5. One thing I want you to remember that all the dipoles together make up the total dipole moment of a molecule. Okay, sometimes they cancel out if they're opposite. Sometimes they add if they're going in the same direction. Okay, all right. That is it for unit 5. Now, next week, I'm going to be getting into, not unit 6, but it's a little bit left over in acids and bases, and that'll be included in the final. Okay, and again, I'll have your tests ready this evening, hopefully sooner than later. And it'll be a test similar to the last ones, about the same length as well. So, any questions?
Not anything to do with